All right, in this lesson, we're going to do rose curves, 10-3 in the notes. All right, so we're on page 11. So to start, we're going to graph sine and cosine like we used to do. So R in terms of T. All right, so we're going to make, so R is like Y and T is like theta or X. So we'll make the Y axis R and the X axis T. All right, so that's 2 times the sine of 2t. So can anyone tell me anything about that sine curve?
Hi, sorry, is there a guidance meeting?
That's all good. And so the 2 in the front, does anyone remember what that tells us about the graph of sine? I can see you guys again, it's pretty great. Well, the 2 in the front needs to have like a max and a min of 2. So there's no vertical shift. There's no like plus a number. So the 2 is the amplitude. So 2 and negative 2. All right. And then if we were to graph one period of sine, because it's not reflected, sine starts on the sinusoidal axis. So one period would look like this. Now, does anyone remember if it's sine of 2t? Like, what's the length of that period? Like from 0, like what would be that mark on the x-axis where it finishes the period? So period is 2 pi over b, and b is the number in front of like x, or in this case t. So the period is pi. All right, so that would be one period. And then if we make 2 pi here, we can graph another period. All right, so that would be the graph of R equals 2 sine 2t. All right, then cosine, R equals 4 times cosine of 3t. So that's going to have a maximum and a minimum of 4. And it will start at the max and then go to the min. So max, middle, min, middle, max. And that right there is 2 pi over 3, because period is equal to 2 pi over b, and b is 3. So if we graphed another period, this would be 4 pi over 3. All right, and actually, so this graph would be like more condensed horizontally if we drew them on the same scale, but we changed the scale. Also, this graph would be twice the height, max and min, but we use different scales. So if we use the same scale, like if we made that 4 and that 4, and like that pi and that 2 pi, then this graph would look more smushed vertically, but this graph would look more smushed vertically. This one would look more smushed horizontally. I said it wrong the first time. All right. So rose curves are in the form A times the sine of n times theta, or R equals A times the cosine of n theta. So now we're going to graph these on a polar grid. All right, this is a rectangular grid, right? X and Y axis, we just called it T and R. Now you're going to graph these on a polar grid. So I'm going to pause the video and let you guys try this on your own for a little bit. And I want you to look for patterns. So look at when you change A. So A is the number in front of sine or cosine, like what changes. And when you change N, what happens here? So I'll give you like 5-10 minutes to do that. All right, and I don't want to spoil the surprise. So if you don't have a TI Inspire, just let me know. And if you don't have a graphing calculator, well, if you don't have a TI Inspire, but another type of graphing calculator, let me know, and I'll show you how yours would work. And if you don't have a handheld calculator, let me know, and I'll show you how Desmos would work. All right, but if you have a TI Inspire, you want to change the graph entry to polar. All right, and then make sure that your graphing angle is in radians. So you may have to hit menu, settings, graphing angle radians, and then type in these different curves and look for a pattern. All right, so I'll pause the video so when you watch this later, you're not just watching dead air. All right, so here's the first one that you should try on your calculator. So that's pretty cool. It's a rose curve. I guess because it looks like a rose. I don't know, it looks more like other flowers, you know, like a daffodil. I don't know my flowers, but I feel like it doesn't look like a rose. But anyway, I digress. So anyone notice anything about how either when you change A or B. So let's start off with A. Like when you change A, anyone notice how that affects the rose curve? All right, so right now it's 5. And if you look at like the farthest point on each curve, 1, 2, 3, 4, 5. So that A will tell you like how long the petals are, right? Now they won't all go like vertically or horizontally. Some of them will go diagonally, but A only affects that. If you make a 1, then it'd be a smaller one with the petal of 1. All right, and then for what is this? We call this B or N. So N. So all right, for sine, when N is 3, we got 3 petals. When N is 4, we got 8 petals. When N is 5, we got 5 petals. When N is 6, 12 petals, 3 in each quadrant. 3 times 4 is 12. 7, 7. See, it looks more like, what is that, a daisy or a sunflower? Yeah, so they just call it sunflower curves. Bias. All right, so I'm gonna write these down here, but the pattern for sine is if N is odd, so like 3 petals, 5 petals, 11 petals. If N is odd and it's sine, then you'll have the same number of petals as N. But when it's even, so like 6, all right, now you're gonna have 12 petals. So you'll have half of that even number in each quadrant, and there's 4 quadrants. So it's like 6 cut in half is 3, and then 3 times 4 is 12. So dividing by 2 and multiplying by 4 is the same thing as multiplying by 2. All right. But for cosine, the rule with A still applies. So we'll go back to just like 2. All right, so for cosine, when N is even, it's the same idea where, all right, N is even, N is 2, so there's double that amount of petals. All right, when N is 4, 1, 2, 3, 4, 5, 6, 7, 8, 8 petals. All right, 6, 12 petals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the clock. That's it. All right, and then when N is even, or when N is odd, there's just the same amount of petals. So that rule also works for cosine. It's going to be facing in different directions. And these rules just help verify that you're doing it correctly. But I'll show you how to graph it without these rules, just by plotting points. All right. So let's just summarize that on our little notes here. Whoa, that's awkward. All right. So if you want to just summarize what we just did. If I write pets for petals, pets. All right, this had 3 petals, this had 5 petals, this had 4 petals, this had 8 petals. 3, 5, 4, 8. So again, if N is odd, then N is the #petals. And if N is even, then 2N is the number of petals. Is petals with a T or a D? Is it like a bicycle pedals a D and a flower petals a T?
Yeah.
Nice. Didn't even have to look that up. All right, and then A is the length of the petals. All right, put the pedal to the metal. So just a quick piece of vocab so we're on the same page, right? If this is a polar grid, all right, so we got those circly things here. All right, we're gonna call this right here the polar axis, or theta equals 0, because when theta equals 0, that's where that angle would lie. All right, so that's the old x-axis. So I'm not going to call it the x-axis. I probably will call it the x-axis, but I shouldn't. It's not the x-axis. It's called the polar axis. And then this here would be like the angle 90 degrees or pi over 2. So this doesn't have a cool name like polar axis. It's just called theta equals pi over 2. So when I say theta equals pi over 2, I'm really just talking about the y-axis. All right. So if we remember if we look back at the calculator, our pictures here, if we look at sine, all right, sine, whether it's 5 or 2 or 3, notice how it's always symmetric over the y-axis. So sine is always going to be symmetric over, so sine wave curves are always symmetric over the y-axis, or theta equals pi over 2. And if n is odd, no, I wrote that wrong. If n is even, then it's also symmetric over polar axis. All right, so what do I mean by that? N is odd on that picture right there. Oh, you can't see what I'm writing because I'm showing my calculator, but I'm just writing what I'm saying. I'll project it in a second. But when n is odd, it's symmetric over the y-axis, or the theta equals pi over 2 axis. When it's even, it's symmetric over both. Like you could flip it over the x or the y-axis and it would flip onto itself. All right. And then cosine rose curves are symmetric over the polar axis if n is odd, and both if n is even. So that's kind of the same deal for both of them, whether it's sine or cosine. If n is even, then it's going to be symmetric over both axes. If n is odd, then it's only symmetric over now the x-axis. So it is slightly different. When n is odd, sine is symmetric over the y-axis, or pi over 2. And when it's cosine, if n is odd, it's symmetric over the x-axis. Right? So again, you're not going to graph these simply based off these rules, but if you have these rules and you can use your notes, then you can check if you're doing it right. And you can also check if you just use the graphing calculator too. But back in my day, we would take tests without calculators and walk to school uphill both ways without shoes in the snow. All right. Some of us are just built different. Just kidding. That's not true. All right. All right. So let's graph some of these. Let's do it. Let's jump right into it. If you didn't get a chance to write this down, I'll post this later. All right. So you got to. This might be uncomfortable for some of you, but just bear with me. We'll get through it together. All right. So when we graph a rose curve, you want to first graph the rectangular version. So we're going to basically graph this like we started, like over an x and y axis, and then take those points and then plot them on the polar grid. Okay. So you have to remember how to graph sine and cosine. All right. R is the y axis that goes from 3 to -3. And theta is the x axis. So that goes, so the period of this will be 2 pi over 2. So it's pi. All right. So that means that the increment is equal to pi over 4. So every tick mark will make pi over 4. So pi over 4. Now, this next one would just be 2 pi over 4. But you're going to want to simplify these because we're now going to graph these on the polar grid. So don't leave it 2 pi over 4. Like simplify that to pi over 2. And this shouldn't be too difficult because we're always starting on the y-axis. We're never going to have like a horizontal shift. All right. So then this would be 3 pi over 4, which can't be simplified. And then 4 pi over 4, which is just pi. And then let's just go 2 periods. So then 5 pi over 4, 6 pi over 4. All right, 6 pi over 4, that's 3 pi over 2. 7 pi over 4. 8 pi over 4, that's 2 pi. All right, so we got our grid set up. Now we can graph. So it's cosine. It's going to start at the max at 3. And then go to the middle, and then the minimum, and then the middle, and then the max. And then the middle, and then the minimum, and then the middle, and then the max. So those are the points that we're now going to take and just plot them on our polar grid. So you don't really even have to do this part, but I'll just with a nice light line, I'll connect the dots. Actually, you should do it because I'm going to explain about that. So you want to know like it's decreasing from 0 to pi over 2 and then increasing from pi over 2 to theta or to pi. All right. So now let's do it. Let's graph this rose curve. All right. You'll remember this day for your whole life. The first time you graph the rose curve. One of your most cherished high school memories. So the first point is at 0, 3. So remember, when we plot that point, we start at 0. So, and because it's r is 3, we move in the positive direction, like where 0 is facing, 3 units. So we go 1, 2, 3. Boom. Okay. Now, pi over 4 is at 0. So anytime you have to plot a point that has a r of 0, I want you to like draw a dotted line through that angle. And then do it in both directions because we know these have symmetry. So this tail will come into play later. All right. So how does that help us? Well, now the next point would technically be at pi over 4, 0. So it's like right at the origin. But to get there, we're not going to draw a straight line. So if you look from theta equals 0 to theta equals pi over 4, r is steadily decreasing from 3 to 0. So like in between 0 and pi over 4, like as we rotate this angle, r is going to decrease. And that's where like that half of the petal comes from. All right. So if I were just to like emphasize that with my zoom marker thing on this one, all right, just so we have more room, just to show you what I just did there. Like, all right, when theta is like here, which would be pi over 12, all right, pi over 12 would be like somewhere right here. So r is like in between 3 and 0, probably closer to 2. So like here it would like, all right, it's the angle's getting bigger, but r is getting smaller. So as the angle gets bigger, like we're getting closer and closer to 0. And that's like how the petal forms. All right. And we'll keep doing that a bunch of times. If that doesn't make sense, we'll keep doing it, but just ask if I'm not being clear enough. All right, now, so anytime you go from a point that is like a positive or negative point to like a point that has r is 0, you're going to want to like kind of make that motion like that petal. And this dotted line helps make sure you don't cross over there. All right, and then the next point is at pi over 2, negative 3. So if we plotted that point, all right, pi over 2 is right here, and negative 3 means we work backwards 3. So like 1, 2, 3. Now, in between pi over 4 and pi over 2, those are these angles right here. But for all those angles, r is negative. So instead of plotting points this way, we're going to go in the negative direction. So like when theta is in between pi over 2 and pi over 4, so like right here, r is going to be like negative, like, like 1.5, somewhere in between. So it's going to end up having like a curve like that down there. So if r is negative, you just go in the opposite direction of where the angle is. All right. Now we're here. We're at, we got a question. Is this a part of calculus? Yeah, I would say so. I haven't taken calculus in like 10 years, but I'm pretty sure you do this in calculus. I don't ever remember, honestly, to be completely honest, I did 4 years math degree at University of Delaware. I have no recollection of ever doing any rose curves.
Then calculus focuses more on like what type of flower.
Yeah, I think you're right. All right, so now we're at 3 pi over 4. So 3 pi over 4 is like right here. So anytime you have a point that has like R0, draw like a dotted line through that point. And then draw it through like its other angle in the other direction. All right, so now when the angle is in between pi over 2 and 3 pi over 4, so like this part, all right, because R is negative, it's going to be like in the opposite direction and getting closer to 0. So it's getting back towards the pole, which is what we call the origin. All right. And then, so that was from pi over 2 to 3 pi over 4. So now we're graphing in between 3 pi over 4 and pi. So that's this little eighth of a quadrant here. All right, so in that case, we're going from 0 to 3. So by the time we get to pi, 1, 2, 3, we should be at 3. So from 3 pi over 4 to pi, R is getting bigger. So that's why we're like, as we're rotating, we're getting farther away from the pole. All right, and we want to keep going till we get back to where we started. And I'll show you a way to know where that is without just getting there. Like you'll know before you start. All right, but now we're here. Now we're at pi. And look, if you did this much and you know, like, all right, this is 3 cosine of 2 theta. So 2 is even, it should have 4 petals. I mean, eventually you could just get this far and then be like, all right, it's going to go like that, and then like that, and then like that. But I'm going to break it down a lot for the first few. All right. But once you kind of see, you have enough information to see like, all right, what this rose curve is going to look like, just you go ahead and do it. All right. So now we're in between pi and 5 pi over 4. So that's this little eighth right here. So on that little eighth of an increment from pi to 5 pi over 4, it's going from positive 3 back to 0. So like as we rotate this way, R is getting closer to 0. So it's going to have like, it's going to finish that part of the petal. All right. And then we keep going. So now from 5 pi over 4 to 3 pi over 2, R is negative. So instead of graphing towards these angles in the positive direction, we're going to graph in the negative direction. And eventually, when we get to 3 pi over 2, R is negative 3. So if we look at 3 pi over 2, and then we go back 3 because it's negative 3, 1, 2, 3, all right, we'll be there. So now that's why this part of the curve looks like that. So it's like if you were like a little person and you were standing here, it's like, all right, you face in the direction of the angle and then you walk out R units. But if R is negative, then you go backwards. That's how I think. I imagine a little tiny person walking along this grid. All right, then now from 3 pi over 2 to 7 pi over 4, so like on this part of it, R is negative, but it's getting closer to 0. So that's why it's going to be like behind those angles and get closer to 0 and look like that. And then from 7 pi over 4 to 2 pi, R is getting bigger from 0 to 3. So from here to here, it's going outwards like that. And there we go. It's a rose curve, baby. The thickness of the petals, if by thickness you mean like how far out this is, that is based on A. But if by thickness you're talking about like how hard I press down on the pen, that just is directly correlated to the amount of anxiety I have as I'm writing these. So there's no rhyme or reason to how thick these are, if that's what you mean by thickness.
Yeah, but those technically ellipses, or are they just something else?
It's a good question. They're not, and if you look at the calculator, you kind of see it better. They're more, I don't think they are.
Like they're more
I'm pretty positive they aren't, but I never thought of it. So yeah, I mean, if you want to use ellipses as like a way to like figure out how you're going to draw it, that's fine. But I wouldn't call them ellipses. They're just petals. All right. Oh, how wide it is. All right, cool. All right, so yeah. Next class, we'll learn about cardioids invented by Cardi B. Rose curves. Anyone know who invented rose curves? It was Doja Cat. Doja Cat.
Someone with the name Rosa something?
No, it was Doja Cat. Yeah. All right. So now let's do another one. Oh wait, let's write these things in because these are important. So notice how this had 4 petals and it took us 8 increments. So 4 petals, 8 increments. All right. So now identify the values of theta. So this got traced out completely after 2 pi. So we're from theta from 0 to 2 pi. And later on, we'll look at these and we'll find a pattern and then we'll see if we can use that going forward. All right, so now let's do another one. Let's do a cosine one. So cosine, this is r equals -5 cosine 3 theta. So our max is at 5, our min is at -5. And so period is 2 pi over 3. So I'm going to graph 2 periods. So I'll put 2 pi over 3 here and then double it for another period, put 4 pi over 3 there. So every increment is going to be 1/4 of that. So that's 2 pi over 12, and that's pi over 6. So if we divide each period into 4 increments, we want to write what those angles are and simplify them so that we can find them easily on this polar curve. So this would be pi over 6, and then keep adding pi over 6. This would be 2 pi over 6, which is pi over 3, and then 3 pi over 6, pi over 2, and then 4 pi over 6, which is 2 pi over 3, and then 5 pi over 6. So I just keep adding pi over 6 and then reducing if I can. 6 pi over 6, that's pi. 7 pi over 6, 8 pi over 6. So do that to make sure you're on the right spot, and 8 pi over 6 does simplify to 4 pi over 3. All right. So now, -5 will start down here, and then go middle, and then max, and then middle, and then min. And there is 1 period. And then middle, max, middle, min. All right. So now let's plot these points. So now we're going to start at 0, -5. So 0 would be here, and 1, 2, 3, 4, +5 would be here. But because it's -5, we got to start 1, 2, 3, 4, 5 in the negative direction. All right. And then we rotate to pi over 6. So anytime you have an angle that has an r of 0, you're going to want to put like a dotted line through that angle to help guide your curve. So as we rotate from 0 to pi over 6, all right, we start off over here because r is negative, and r is now getting closer to 0. So it's still negative, so it's still like behind this angle, but it's getting closer to 0. So then that creates like that petal. And another thing, Hayden, like, I don't think these petals are perfectly symmetric either, like an ellipse. I'm pretty sure they're not. I'd be surprised if they were. But, you know, I get surprised a lot, so who knows. All right, so now from pi over 6 to pi over 3, we're going to be working up towards 5. So 1, 2, 3, 4, 5. And then so we're going to, as we rotate out, r is getting bigger. So it's going to go to there. And then pi over 2, that has an r of 0. So we're going to draw that axis, or we're going to overlap that like that. So as we go from pi over 3 to pi over 2, r is getting closer to 0 again. So as we rotate, we're also getting closer to 0. Where's that noise coming from? Outside? Sorry. I thought it was coming from over there at first. I was confused. Like the outside by the window. All right. Okay. So where are we? We're here. So we're at pi over 2, 0. Then from pi over 2 to 2 pi over 3. So 2 pi over 3 is over here. All right. We get to negative 5. So because on this interval from like pi over 2 to 2 pi over 3, r is becoming more and more negative, we're going to graph like behind that. So it's going to, so 2 pi over 3, the angle behind that is 5 pi over 3. So we go 1, 2, 3, 4, 5 that way. And as we rotate, we end up right there. All right, so keep in mind the rules from before, like this is cosine of 3 theta, so there should just be 3 petals because it's odd. There's something else I was gonna say too, but I'm distracted. 5 pi over 3. Oh yeah, so remember back early, this might help some of you. Remember back this little rule here, which I didn't really focus on super hard, but I'm kind of using this, like when you have a negative r plus theta, it's the same thing as r theta. So r theta is equal to negative r theta plus pi. So I'll show you what I mean, how it relates to this. So right here, we're plotting this point, which is 2 pi over 3 comma negative 5, but I wrote it in reverse. So negative 5 comma 2 pi over 3. So that, according to that rule, is the same thing as positive r, but 2 pi over 3 plus pi. Which, if you look at 2 pi over 3 and then go plus pi, we end up right over here at 5 pi over 3. All right, so if it's weird, me going in reverse when I'm rotating, you could always just take any polar coordinate that has a negative r and just convert it to a positive r by just adding pi to the angle, all right? So that's why I'm plotting that point here at 5 comma 2 pi over 3 plus pi, which is 5 pi over 3. All right, so now we're here, all right, but we're really here at 2 pi over 3. Now we go to 5 pi over 6, which is at 0. So I'm going to put the dotted line through there. All right, and then at this point, like, if you kind of see what's happening with the curve, you could see, all right, well, this is just going to go back because from 5 pi over 6 to pi, so on this interval, r is negative, but it's getting closer to 0. So we're going to like get closer to 0 in the negative direction over here. And then from 5 pi over 6 to pi, r is growing. So as we rotate, we're getting farther away. And now we just completed the curve. And if you're confused, like, well, why are there empty spaces here? If you're not sure if there should be a curve there, then that's when you will go to these notes here and you see, all right, like if n is odd, that's the number of petals. So in this case, n is 3, so there should be 3 petals. So we know that we did it right. All right, now in this case, we had 3 petals. And we finished at pi right here. So for 3 petals, that was 1, 2, 3, 4, 5, 6 increments. So if we're noticing a pattern, if you know how many petals there are, then you double that. So like each petal is 2 increments. So 3 petals, 6 increments. Then you know when you're graphing this, you can just stop after 6 increments. If this is like a little thing you can notice to save your time. All right. And then what values of theta was it traced out? It was traced out from theta to pi. All right. So let's see. We only got a few more. Let me do one more really quick. Sine, let's see. This one's pretty normal. Yeah, let's skip that one and we'll go right to D. You know what? I'm going to use what I already wrote out here, and I'll write on top of it. So for D, all right, we have R is 7, so we go like from 7 to -7. And our period is going to be 2 pi over pi, 2 pi over 2. So it's just pi. So that's one period. And then our increments are 1/4 of that. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and then you just simplify it. So pi over 4, 2 pi over 4 is pi over 2, 3 pi over 4, pi can't be simplified, neither can 5 pi over 4, but 6 pi over 4 reduces to 3 pi over 2, 7 pi over 4, 8 pi over 4 is 2 pi. Now, since it's sine, we start on the sinusoidal axis, and since it's not reflected, we go up, middle, down, middle, max, middle, min, middle. So now when we're graphing this, all right, we start on the pole because we're at R0. And then to pi over 4, we're going to go all the way out to 7. So as we rotate, R is getting bigger. So as we rotate, we're getting farther away from the pole. And then from pi over 4 to pi over 2, R is approaching 0. So as we rotate from pi over 4 to pi over 2, we're getting closer and closer to the pole here. And now we have a point at 0. Now we started at 0, so we could have done this one earlier, where we highlight the x-axis. And then for pi over 2, all right, now because that has a point of 0, we're gonna highlight the y-axis so we can guide our curve. And then now for 3 pi over 4, so here, R is getting negative. So like in this area from pi over 2 to 3 pi over 4, we're getting farther away. We're going towards -7 or towards 7 in the opposite direction. And then we get to 3 pi over 4 comma -7, which is the same point as +7 comma 7 pi over 4, because that's 3 pi over 4 plus pi. All right, and then from 3 pi over 4 to pi, as we rotate here, we're getting closer back to 0. So from negative to 0. And now we're at pi is equal to 0. And then from pi to 5 pi over 4, R is getting bigger. It's getting closer to 7. So from here to here, we're coming out. And then from 5 pi over 4 to 3 pi over 2, it's getting closer to 0. So we come back this way. And then 3 pi over 2 is going this direction. So we're at the pole, but as we get closer to 7 pi over 4, R is getting more negative. So we're gonna go in the opposite direction. And then from 7 pi over 4 to 2 pi, it's getting closer to 0. So we're coming back towards the pole. All right, so that would be 7. So it's 7 units out each petal. 2 pi, there's 4 petals. And remember, when n is even for sine, it's gonna be symmetric over both axes. All right, so those rules help. And then this one here is just, we did that earlier. That's just a circle tangent to the x-axis, but you can graph it like the same way that we did. It's just gonna have like one circular petal. So we basically got through everything. So I know I didn't really go over E and C. So tomorrow you have the whole period to work on the homework, which is on Classroom. All right, so I'll be on Zoom all period. So if you want me to go over more of these examples, whether from the notes or the homework, just let me know. All right.